Well, in this video we're going to be talking about proofwriting just a little bit and just introducing the idea of proofwriting. Now, as we've talked about this before, when we have propositions we have to prove them. Of course, postulates don't require proof. They're accepted as true without proof, but propositions, theorems, have to be proved. And there are different styles we can go at with proving these, but we're going to be using a multi-column approach to writing our proofs, at least for most of the semester, because this is a good pedagogical tool. It's a good tool to help students learn how to write proofs to begin with. So this is a good tool that you can use with your high school students, those of you who are going on to teach junior high and high school geometry. It's also a very good tool to help us understand the structure of a proof. And so, even though this is maybe not a most mature way of writing proofs in a professional mathematician sense, it is certainly an excellent way to get to understanding proof. So we're going to do this. We're going to have we'll probably just have at least 3 columns here. And the first column here will be just step numbers, 1, 2, 3, whatever. Then we'll have statements. Statements are statements that we're going to say things that are true about our situation. They may be conclusions from earlier work. Justifications or reasons will be given for every statement. By putting it in a column format like this, we're guaranteed that if we fill in the blanks right, we're guaranteed that we have provided a justification for every single statement that we have. Also, what are allowable for justifications? Okay, so justifications should be provided for every step, and those justifications can only use the following: something that's given in the hypothesis of a theorem, a previous statement in the proof, a previously proved theorem, a definition, a postulate, or some rule of logic. And typically there'll be combinations of those things. So the first statement, the reason or justification, is almost always given in the hypothesis. So a theorem will usually say, if certain things happen, then something else is going to happen. So that first set of things that you say, if blank, then second blank, what's in that first blank is called the hypothesis of the theorem, and the second blank is the conclusion of the theorem. The last statement will certainly be always the conclusion of the theorem, and usually the first statement is one or more of the hypotheses given in the theorem itself. So the statement that you start with will be something that's given. That's going to be your justification. From there on, we're going to be using those statements along with postulates and so forth to continue on with the proof. So we notice that we're going to use a theorem. Most of the time, a previously proved proposition or even a postulate are in if-then format. Notice there's statements that have a hypothesis and a conclusion. You can't use that postulate or theorem unless you've already established the hypothesis at some point. Either it's some earlier statement. So we may go along here, and the statement, step 1 will be some statement. The reason is, or justification is, given in the hypothesis of the proposition. Statement 2 will be something, and the justification will be step 1, the statement from step 1, and that step 1 will satisfy the hypothesis, say, of a postulate, say postulate 2 or something. And so the justification will be statement 1 with postulate 2, and then the statement 2 then will be the conclusion of the postulate that we are using as a justification. So we have, in our justifications, we should be referencing earlier steps and a postulate or definition or theorem or something that's been proved earlier. In the case of propositions, it has to be proved earlier so that we avoid circular logic. but we can also refer back to postulates or definitions. Now, when it's all said and done, we should have a series of steps that come along here, and eventually one step leads to the other, and finally we get to the end, and the last step is the conclusion, not only of some proposition from earlier or some rule of logic combining steps from earlier, but it's also finally is the conclusion of the theorem that we're trying to prove. Now, when you look back at it, you should have used every single step in the proof, except for the very last one, as a reason for one or more of the subsequent steps. If you're not using it, one of two things happens. Either one, you've done everything correctly, but you've got a step there that you don't really need. If it's not used later in the proof, it's not a needed step. You could erase it. Or what's more likely, in my experience, is a student really did use it later on, but just didn't document it correctly. And so look for where you actually use that step later on. So every step should be used later on as a justification. Secondly, we have to make sure that every statement is very carefully justified, and the multi-column format like this is very helpful. Now, the other thing that you can do with we're going to be writing these proofs. We'll set up a table like this in Geometry Sketchpad. In fact, you can just copy this one and paste it in when you're writing a proof. No proofs to be written this week, but we'll start writing proofs, filling in the blanks for some written proofs and partially written proofs, and then also writing our own proofs starting next week. And you can just copy this and then start filling in the blanks. Now, what we'll do here in Sketchpad is the steps will be linked to hide-show things. So it'll start out, and you'll look at it. If you open the proof up, you'll just see the table, and you'll see numbers 1, 2, 3, 4, 5, 6, 7, whatever, down to the end, and you'll see nothing over here. And when you click on step 1, I want the statement and the justification to appear, but also along with that will be a dynamic illustration that will appear off to the side. And so each step, as you click it, it will show you the constructions or markings on the constructions that relate to what we have here. And the constructions should be dynamic enough that we can look at all examples basically by dragging around and manipulating the expression. This will give us nice dynamic illustrations of our proofs. Now let's talk some more about diagrams and proof. Diagrams, drawings, and constructions. So on one level, visualizations, including the dynamic and static diagrams, drawings, and constructions, are superfluous in the study of geometry. So by that, what do I mean by that? Well, in a formal study of geometry, the proof of the proposition, and if you have problem solving, solutions to problems, cannot rely on the visual illustration. They must be complete on their own. Okay, so you should be able to erase the pictures and completely rely on the proof. The proof should not rely on any information that's in the picture. It should stand on its own. And in fact, the proof might be actually valid for several completely different visualizations. For example, it might be valid for a visualization in Euclidean geometry and for a completely looking visualization in Euclidean, say, hyperbolic geometry, or maybe two completely different models for hyperbolic geometry may look different, but the proof still holds in both cases. Okay, so on the one hand, pictures, drawings, constructions, those are extra. The proofs stand on their own. So you could actually do geometry without any drawings whatsoever. Okay, now that being said, one of the most beautiful things and useful things about geometry is its visual aspect. And the visuals can often provide insight, inspiration, and ideas for proofs and counterexamples. And so how we visualize the geometry is going to affect how we create it, what we know about it, and it's going to inform us and illustrate what's going on. That's also true for other areas of mathematics, but it's especially true for geometry. Now, one of the things that is important is our visualization of what an object looks like. And I went to a math education talk one time, and the topic of the talk was what one's canonical view of an object looks like. And they did things like asking people, well, what does a parallelogram look like? Well, it's and basically people gave descriptions of it, and they were based on whatever static picture was in their textbook or that their teacher used as an example. So, for example, many of them thought of a parallelogram as a horizontal and vertical side that were parallel, and then two slanted sides, and it was always slanted to the right, so they had positive slope on those sides. And maybe even they went so far as to say, well, it's green or it's blue. Well, that's because that's what color it was in their textbook. So, of course, some things are built in the definition of a parallelogram. For example, that it has opposite sides parallel. That's the definition. But some of the other things, like being blue or slanting to the right or having horizontal and vertical sides, those are not properties of a parallelogram. But if that's what you have in your mind, you may start to assume those sort of things. What we want to do in this course is we want to start thinking of objects as being dynamic. And we want to be able to think of these objects moving around and morphing from one example to another. And in the process of these things morphing around, we can see what properties are retained and which properties are changed. Okay, so Geometry Sketchpad is going to allow us to experiment and discover properties, making test conjectures, and to dynamically record and illustrate proofs, but it will also allow us to test thousands of examples at once. Okay? And so, in theory, infinitely many examples. So, one of the things that we can do is we can do a process of constructing something with certain properties, morph it around by manipulating it in Geometry Sketchpad, and we can come up with, many examples, and we can notice what properties change and which properties stay the same. And that can help us, convince us, if it's false, it'll help us actually come across a counterexample. And if it's true, for whatever conjecture we have, we can go along and come up with maybe, it'll convince us it's true, and perhaps we'll even come up with an idea of how to prove it. So notice that this gives us a level of convincing that's between one example or a couple of examples and a real proof, a formal proof. We can be convinced by lots of examples in Sketchpad if we're sure that it's been constructed correctly. Now, so when we write a formal proof in this context, it's not so much about how to convince us that it's true, although we shouldn't be, as mathematicians, we shouldn't be completely convinced it's true until we see that proof and work through it. But yet that proof is then more about, rather not so much to convince us, but rather to explain why the proposition is true and how it works and what is it that's making that work. Okay, so drawings are very important. Our proofs need to be complete, and our descriptions in our proofs have to be complete enough that they don't refer to the drawing, but at the same time we will refer to the drawing in our thinking of it in our illustration. Now, one more thing is very important in Geometry Sketchpad. We may need to make a careful distinction between what I'm going to call a drawing and a construction. Give me just a second to pull up another Sketchpad file, because in the tutorial I talk about this some. And I'm not going to be able to get to it very quickly because I don't have it here on another hard drive. Okay, well, I'll do the illustration whenever we'll look at that when we look at the tutorial. But if you have an object that's constructed, it can be morphed around. And so you may have something that temporarily looks like or maybe even temporarily is, some other object. So for example, let's just draw a triangle right here. Well, it might be, at the moment, this might be, if I get it just right, that might be an equilateral triangle. Okay? But is it really an equilateral triangle in Sketchpad? At the moment it's an equilateral triangle perhaps, but as I change it, maybe it's no longer an equilateral triangle. This one looks like it might be isosceles, but is it? Well, not necessarily, because as I drag it around, I do the drag test, we see that it doesn't stay isosceles. So this is an example of actually a general triangle. Okay, and so as you manipulate it, it stays a triangle in this case. Okay, as I drag the points around and move things around here. But it doesn't, but we can get any triangle, so it's a general triangle. On the other hand, if I constructed this in such a way that it was isosceles triangle, even though it might temporarily be equilateral triangles are isosceles triangles, as we move it around, it may change to a non-equilateral triangle that is isosceles. But I could never change it to where it was not isosceles triangle if it's constructed correctly. So there's a difference in what I'm going to call drawing something. So this might be drawing something that is an isosceles triangle versus constructing it so that it stays isosceles whenever we work with it and manipulate it. So all your Sketchpad sketches must pass the drag test. I got to be able to drag the points around and drag the control objects, the points and things around, and it still must maintain the properties it's supposed to be. Now, for example, if the problem is, or task is to construct an isosceles triangle, if you make it so that you drag it around and it's always an isosceles triangle and we can get every possible isosceles triangle, then you've done the right thing. But you could build in too much or too little structure. If you don't build in enough structure, you may drag it around and it stays a triangle but not isosceles. That's not enough structure. On the other hand, if you build in too much structure, you might make it where it always stays equilateral. Certainly it's staying an isosceles triangle because equilateral triangles are isosceles, but it's not getting any isosceles triangles. So there's an example where too much structure has been built in. So you have to get exactly the right amount of structure built in when you're doing things, sketches, constructing objects in Sketchpad. We'll talk more about that in the tutorial. Now, let's also talk a little bit in this video about rules of logic. So there's certain basic rules of logic, and these are the 12 that are outlined in the text by Greenberg that I brought over here. So the first one goes over what we've already said about what can you use in a proof of a theorem. Well, you can say that for justification. So the justification can be by hypothesis, or in other words, it is given in the hypothesis that this is true. And then by unless it's an existence postulate, postulates are in if-then form. So you can also, if you're going to use that postulate, you also have to refer to which step earlier in the proof you establish that hypothesis. So if we're getting ready to do step 4 and back in step 2, you establish the hypothesis of the postulate we want to use. We might say, well, by step 2 and postulate 6, that's the reason for that conclusion. If it's an existence postulate, of course, there's no hypothesis. It just says by postulate whatever, there exists something. But of course, there are not many of those. We can do the same thing with a proposition if that proposition has previously been proved. So by step 4 and proposition 8, that's we have the result. So step 4, of course, would then be the hypothesis of proposition 8, and whatever step we're on would be the conclusion. Okay, by step so-and-so in definition, we can also use definitions in the same way. Remember, definitions work both directions. And then by step something in a rule of logic, so we can use these other basic rules of logic. So some other things here that we have number 2, proof by contradiction. So one way we can prove P implies Q is to, of course, assume P, the hypothesis, but then assume the negation of Q, and then reach a known contradiction. The statement is both true and false. And when that contradiction is assumed, we know that the assumption that P was false that Q is false is itself false, so that Q is actually true. So P does imply Q. The negation of P is this, tilde P there, squiggle P, and that has the opposite truth values of P. And step 3, the property is that the negation of P is P. So two negatives make a positive. And one of my favorite stories, I was reading about this, I thought this was pretty cute, that mathematician was talking to his daughter about this and said, notice, daughter, that if you've got a negative and a positive in either order, you get a negative. And two negatives, though, make a positive. But there's no way for two positives to make a negative. And, of course, the daughter said, yeah, right, Dad. Of course, what they didn't take into account was there's two positives that just made a negative. And, of course, they didn't count for sarcasm. Not accounting for sarcasm, two positives don't make a negative, but two negatives do make a positive. Alright, so number 4, the negation of P implies Q is equivalent to not P and not Q. The negation of P and Q is the same as not P or not Q. And if S of X is a statement about X, a true-false statement about X, if you want to say for every X this statement is true, the opposite of that is equivalent to there exists one X and X, at least one X, such that the opposite of the statement is true. Number 7 says, if you take the statement there exists an X, that should say, let me fix that, an X such that S of X is true, the negation of that is for every X the negation is true. Number 8 is if P implies Q and P are steps in a proof, they can be used as justification that Q is a valid conclusion, one of your statements. We also have the following. P implies Q and Q implies R implies that P implies R. So that's a sort of a transitivity there. P and Q imply P. If P and Q are true, then certainly P is true. And of course you can also say that means Q is true. Not Q implies not P if and only if P implies Q. So if P implies Q as a statement, then not Q implies not P is what's called the contrapositive. And so the contrapositive and the original statement are logically equivalent. Number 10, for any statement P, the statement P or not P is a valid statement and a proof. And so that basically means that we can divide an argument into cases, so we can generalize that a bit in number 11. So if we've already established a set of sequence of statements, S1 or S2 or up to Sn, one of those is at least true, okay, then we can take those one at a time and argue that S1 implies a statement C is true, and then we can argue that S2 implies C is true, all the way up to Sn. And if we show it for every case, then we can definitely conclude that C is true. That's sort of argument by dividing into cases. And then finally, equivalence. Equality is an equivalence relation. So maybe you've seen this in your classes before. An equivalence relation has 3 properties. It's reflexive, symmetric, and transitive. So reflexive means that every element is related to itself. Symmetric says if X is related to Y, then Y is related to X. And transitivity says if X is related to Y and Y is related to Z, then X is related to Z. So that's an equivalence relation, and equality is our basic example of that, our canonical example. Two things are equal to them. Anything's equal to itself. If X is equal to Y, then Y is equal to X. If X is equal to Y, Y is equal to Z, and X is equal to Z, that's transitivity. These things are closely related to some of what Euclid would have called primitive notions, I think. We also have the ability to do substitution. If S is a statement that's true about X, and X equals Y, then the statement must be true about Y. So I kind of went through those very quickly. Hopefully you've studied these kinds of steps in your earlier classes such as maybe introductory discrete mathematics and or foundations of mathematics, or some similar course, or maybe even in your high school geometry course as well. And another thing I want to do to wrap up this lecture is notice that some of the properties involve qualifiers. So qualifiers are things like at least, at most, exactly, for all, and so forth. You need to pay special attention to these qualifiers. So if you say given two lines there exist at least 3 points in their intersection, that's completely different meaning than there exist at most 3 points, or there exist exactly 3 points. All three of those things have different meanings. Okay, so it makes a big difference when you put those in there. Okay, and I hope that in a previous course you spent some time carefully working through and justifying, maybe with true tables and so forth, some of these properties, and have used them in some other types of proofs. But we're going to be using this type of logic in our geometry proofs. Finally, let's go over some symbols for logic. The negation of P is abbreviated with that little squiggle P, tilde P. If P, then Q is sometimes abbreviated P, arrow Q. IFF stands for if and only if. There exists an X is abbreviated with that little, sort of like a backwards capital E and the X. Alright, here we are, right here. There exists a unique X is abbreviated there exists and an exclamation point. P and Q is P caret Q, like that. Kind of like intersection, because intersection and go together. Intersection of sets and logical and are very similar. And or is like a logical, or is very much like union. So PRQ is abbreviated P, kind of like a little V, Q. And finally, let me remind you that or is an inclusive or, so it does include the possibility that both P and Q are true, then P or Q is true. The only way you can make P or Q false is for both P and Q to be false. So the negation of P or Q is not P and not Q. I believe that was one of our statements up above. P and Q, the only way that to be true is for both P to be true and Q to be true at the same time. So the negation of that is either P is false or Q is false. Okay, so that gives you a little bit of an idea of proofs, rules of logic, a little bit about role of diagrams in proofs. I think that'll wrap us up for this particular lecture.